Voyager never spoke directly to humanity. The photographs that transformed our view of the solar system did not arrive as clear messages from a distant spacecraft. They reached Earth as radio whispers, so faint they were almost indistinguishable from the background noise of the universe. Long before anyone could celebrate those images, something on Earth first had to hear them. Mission control fills with applause as pictures from Voyager appear on the screens. Jupiter's storms, Saturn's rings, the icy worlds beyond. The spacecraft seems almost alive, carrying on a conversation across the darkness, as naturally as a satellite passing overhead. Only one detail remains invisible. Nothing in those celebrated moments reveals who is actually listening. The spacecraft keeps moving farther away. Its radio waves spread outward in every direction. Every additional kilometer dilutes the signal, leaving less and less energy for Earth to collect. At first, the loss is barely noticeable. Eventually, distance begins to dictate an entirely different set of rules. A transmitter no more powerful than a household refrigerator light bulb continues broadcasting from billions of kilometers away. That sounds impossible. Yet the spacecraft is not cheating physics. Physics is becoming the problem. As the probes leave the inner solar system, their signals weaken according to one of nature's simplest laws. Double the distance, and the received power falls to 1/4. The spacecraft does exactly what it was designed to do. Space itself quietly overwhelms the transmission. Ordinary tracking stations are no longer enough. The first consequence is not silence. It is delay. Pictures arrive more slowly. Scientific measurements take hours to transmit. Every bit becomes expensive because every bit must survive a journey across an expanding ocean of empty space. When Mariner 4 flew past Mars in 1965, its first close-up photographs returned at only about 8.3 bits per second. A single image required more than 8 hours to reach Earth. Getting to another world was only part of the challenge. Bringing that world home was something else entirely. Engineers began looking down at maps instead of up at rockets. California, Spain, Australia. 3 locations separated by roughly 120 degrees around the planet. As Earth rotates, one station loses sight of the spacecraft just as another acquires it. The handoff happens quietly. Somewhere, one giant antenna stops moving. Thousands of kilometers away, another begins turning toward the same invisible point in the sky. On December 24, 1963, NASA formally separates deep space communication from the systems designed for satellites orbiting near Earth. The Deep Space Network is born, not because rockets have changed, but because distance has. The dishes dominate the landscape. Steel structures rising above the desert. Massive parabolic bowls turning slowly beneath open skies. From a distance, they resemble monuments. In operation, they behave more like ears. One of the largest. Deep Space Station 14 at Goldstone weighs nearly 2,700 metric tons. Even so, it must point with extreme precision toward the place where the spacecraft will be when its radio signal finally arrives, many hours after leaving the probe. The target cannot be seen, only calculated. Even an antenna that large cannot solve the problem by itself. Inside the receiver, another obstacle is waiting. Every electronic component produces a small amount of thermal noise. Left untreated, the equipment on Earth generates enough interference to bury the spacecraft beneath the receiver's own background hiss. The signal has reached Earth. Earth still cannot hear it. So the engineers changed the receiver instead. Liquid helium chills a Ruby Maser amplifier to about 4.5 Kelvin, only a few degrees above absolute zero. The hardware becomes quiet enough to separate an artificial whisper from the natural radio noise surrounding the planet. The machinery does not make Voyager louder. It makes Earth quieter. That difference changes everything. Signals arriving with powers of roughly 1/10 quintillionth of a watt become recoverable. Data that would otherwise disappear into static begins forming images, scientific measurements, and engineering telemetry. The giant antenna appears again. Now it carries a different meaning. Its immense steel frame is no longer impressive simply because of its size. Every additional meter of collecting surface allows Earth to gather a little more of an unimaginably weak signal. As Voyager travels farther outward, the ground must become more capable in return. Between 1986 and 1988, flagship antennas expand from 64 meters to 70 meters in diameter. The added collecting area prepares the network for Voyager 2's encounters with Uranus and Neptune. The spacecraft keeps traveling. On Earth, the listening grows stronger.